Before the 1800s, most people in Western cultures thought about the Earth as described in the Bible, formed in about 6,000 years, and pretty much unchanged since it was originally formed. Almost all the layered rocks on Earth were explained as a consequence of Noah's flood, and the fossils that were found within them were supposedly drowned by the great flood waters. This quote from John Woodard in 1695 is fairly typical of the thinking of that period. The terra-aqueous globe is to this day nearly in the same condition that the universal deluge left it, being also like to continue so till the time of its final ruin and dissolution, preserved toward the same end for which it was first formed. But just how old was the Earth? Typical of the thinking of this time was an attempt by James Ussher, Archbishop of Armagh in Ireland, to calculate the age of the Earth using the Bible. In 1650, he calculated the Earth was formed in 4004 BC. He did this by looking at the ages of the patriarchs as described in the Bible, when so-and-so begat so-and-so when he was so many hundred years old, and so on. But of course, the Bible doesn't give a complete record of all the events since creation, so he used a lot of other kinds of scholarship to try to get his estimate of 4004 BC. Today, we look back at this with amusement, but it was cutting-edge scholarship for 1650, and there are still people today who believe the Earth is only 6,000 years old. Another debate of the time was the nature of fossils. How were they formed? Were they pranks of the devil, sports of nature, or lusus naturae? Were they divinely created? This was a very significant debate because although some fossils, like shells, look familiar to anyone today, others, like the bullet-shaped shells of belemnites or the little lifesavers of crinoids, were not obvious to scholars of the time. A key figure in this debate was this man, Niels Steensen, better known today by a Latinized version of his name, Nicholas Steno. Born in 1638 in Copenhagen, he was raised a Lutheran, but then took medical training in many of the leading capitals of Europe. In 1666, he became the official doctor of the Grand Duke of Tuscany in Florence, one of the Medicis, Ferdinand II. In this post, he had the opportunity to walk around the Apennine Mountains to the east of Florence and see many fossils in the rocks. One day, a large shark was caught by fishermen in the port city of Livorno and was sent to Florence for Steno to study. Steno noticed something interesting. The teeth of the shark closely resemble what scholars have been calling tungstones or glossopetri. The origin of these tungstones was controversial. Some thought they were formed by lightning bolts, but Steno realized that tungstones were not supernaturally produced, but simply fossils of shark teeth. If fossil seashells and shark teeth had been found inside a solid sandstone, how did they get there? Steno proposed a novel solution. In 1669, Steno published Prologue to a Dissertation on a Solid Naturally Contained Within a Solid. The title sounds odd until you realize that most people at the time thought that the fossils and the rocks that surrounded them were both created together at the same time. Steno argued that shells and shark teeth came first, as the soft sands or muds that surrounded them and the sedimentary rock had come later, and therefore there was a sequence of events. They were not all created at the same time. This insight is the beginning of what we now call relative dating in geologic time. One event is younger than or older than another. This led to another insight. If the hard sandstones and mudstones of the Apennines were once soft, liquid sands and muds, then they too had a relative sequence of age. One would be younger or older than another. These sketches are the only published figures from Steno's work showing his concepts. Today we call them Steno's laws. There are 4 basic techniques for determining the relative age of different geologic events. The first of these is superposition. In an interlayered sequence of rocks, you have to have the older rocks on the bottom before you can deposit younger rocks on top. In the Grand Canyon, the oldest rocks in this layered sequence are at the bottom, and the youngest ones are at the very top. It's analogous to the pile of papers on a messy desk. If you don't disturb the piles, then the stuff that's oldest will be near the bottom of the stack, while the stuff you dealt with most recently will be near the top. The second of Steno's principles was the law of original horizontality. If you look at modern sands and muds being laid down on the bottom of rivers and oceans today, they always form horizontal layers, thanks to the influence of gravity. If you find them deformed or tilted in any way, then there must have been some kind of force that has tilted them since they were formed. A third idea is the principle of original continuity. If beds are laid down in continuous flat sheets in horizontal position, then when you find them cut by river or stream at later time, then you know that they once connected across and later erosion has cut them away. Again, by relative dating, the erosion is younger than the beds. For example, here in the Grand Canyon, the white layer that the person in the foreground is sitting on matches a white layer you can see on the far distant top of the other rim. Today, we routinely connect the two mentally across, but this was a huge insight for 1669. The fourth insight is cross-cutting relationships. If you have one object cuts across another, like an igneous rock or a fault cuts across a previous existing rock, then the thing that does the cutting must necessarily be younger than what it cuts through. These four principles from 1669 now are the foundation for modern stratigraphy and allow us to reconstruct how geologic time has taken place. Ironically, Steno himself never followed up on his great insights. A year after he published his prologue, or prodromus, he converted to Catholicism and became eventually a Catholic priest. He then stopped doing science and never got around to writing the actual dissertation for which the prologue was written. A word to the wise: never publish part 1 of something without having part 2 written and ready to go to press. As a Catholic priest, the Pope appointed him to become the titular bishop of a region that was then called Tidiopolis, which is now part of Turkey and had no Catholics. Instead, he became a prominent Catholic scholar and is now considered both a saint by the Catholic Church and also one of the founders of geology. But the breakthrough in understanding geologic time in the age of the Earth was due to this man, James Hutton. Born in Edinburgh, Scotland in 1726, he attended the University of Edinburgh, where he both trained in the law and also in medicine. He was a particularly good chemist, so his discovery of a technique to make the valuable salt sal ammoniac actually made him good money. But instead of following careers in law or medicine, he went back to his family property, Sly Houses, in eastern Scotland, and became a very active landowner, focusing on techniques for improving agriculture and understanding how his property would be made more profitable. He applied the latest techniques in soil management and soil drainage to his properties, and yet, as he wrote in a letter in 1753, he had, quote, become very fond of studying the surface of the earth, and was looking with anxious curiosity into every pit or ditch or bed of a river that fell his way. In particular, he was fascinated with the way which rivers and streams deposited layer upon layer of sediment, each event representing a few days to a full year, and that if you had a sequence of hundreds of these layers, you must have thousands of years represented. If we could use modern processes to understand events in the geologic past, a principle known as uniformitarianism, then Hutton realized that a stack of thousands of feet of sedimentary rock represented an immense amount of time. In 1768, Hutton leased out most of his property at Sly Houses to tenant farmers and moved back to Edinburgh, which was a bustling city in those days. It was in the early phases of the Industrial Revolution and also in the early phases of what is now known as the Scottish Enlightenment. Unfettered by the oppression of a very powerful church, unlike most countries in Europe at the time, Scotland was a hotbed of intellectual ferment. As a gentleman scholar, Hutton hung out with his good friends who were part of his social circle at the Oyster Club. These included not only James Watt, the inventor of the first modern practical steam engine that powered the Industrial Revolution, but chemist Joseph Black, who was one of his closest friends, as well as the famous economist Adam Smith, author of The Wealth of Nations, the founding document of capitalism. These educated gentlemen met regularly in the pubs to exchange ideas and talk about nearly anything. Nothing was off limits. Hutton focused on the stuff about the earth that he had first thought about as a gentleman farmer at Sly Houses. He visited outcrops all over Scotland and finally began to write down his ideas, which were presented to his fellow scientists in 1785 and published as a book in 1788 called Theory of the Earth. One of his key discoveries is the significance of what is now called an angular unconformity, where a series of rocks has been formed in horizontal layers, then turned into hard rock, then tilted on its side, then eroded, and then covered up by another sequence of rocks at an angle. Hutton realized that unconformities, like this particular example in Jedburgh in Scotland, must represent enormous amounts of time, from the time of the deposition of the original layers, to turning them to hard rock, to tilting them on their sides, then eroding them off, then depositing a new set of layers on the sharp erosional surface. On one of his very last geologic excursions, Hutton found the perfect example at Sicker Point on the eastern coast of Scotland. At Sicker Point, you have a series of vertical rocks, which used to be horizontal, eroded down, and covered up by another series of rocks which are nearly horizontal. If you apply uniformitarian principles to this outcrop, then each of those tilted layers represents a long period of time of deposition. Now, more time represented by tilting, more time represented by erosion on the top, and then more time represented by the sequence deposited above the erosional surface. There is no way this could have formed in a mere 6,000 years. As Hutton wrote in 1785, the result, therefore, of our present inquiry is that we find no vestige of a beginning, no prospect of an end. Hutton had shown that the earth was immensely old, so old there was no vestige of a beginning. As his friend John Playfair wrote, the mind seemed to go giddy by looking so far into the abyss of time.